I will share my screen. So let me know if you can see my screen.
Yes.
So can you see my screen?
Yes.
Okay. So thank you to the attendee to join this webinar about the Meshless CFD tool, which is Particleworks. So the objective of this webinar it is to present you Particleworks, which is good meshless CFD software for simulation of liquid flow based on the MPS. So MPS stands for particle simulation method. So this webinar will be firstly presented by Michele Merelli. So Michele Merelli, it is a project engineer in Engisoft from Italy. So it's also a Preprocessing manager for Particleworks in Europe. So it is an expert on this Meshless CFD tool. So my name is Didier Zefack. So I am multi-physics simulation on different tools like Geomet. So Geomet is this electric motor design tool. So I will try to show you some demo on that after the presentation and demonstration of Michele. So Michele, maybe I can make you presentator.
Yes, please. Thank you, Didier, for your kind introduction, and good morning, everyone. So the structure of this webinar, I will show you the agenda in a moment, but the idea is that we will.
So I think you can share your screen.
Yeah, 1 second. Okay, good. Can you all see my screen now?
Yes, I can see your screen.
So the agenda of today's meeting is first to give you a little bit of an introduction of moving particle simulation and Particleworks and the advantages over other traditional tools. And then I will go through a lot of application, a lot of fields where Particleworks can show its strength. Lubrication, of course, is the historic milestone. Let's say the first application for Particleworks is lubrication in gearboxes. E-motor cooling, very important application that right now it's increasingly of interest. And as you can see, we will give some present some test cases in collaboration with important players. Then I will mention, of course, the coupling with JMAG and how we can, let's say, transfer the files, the information, namely the HTC information, the transfer coefficient maps, to a JMAG solver to perform the thermal analysis, let's say. Other applications are piston cooling, hydropower generation, and also the field of food and beverage. So we will cover all of that with some example, just to give you an idea of all the fields and yeah, what are the capabilities really of the software. In the final part of the presentation, I will present some advanced feature of the software that could also be of interest for you. And then we will do, let's say in the second half an hour, a live demo, just to give you an idea of how fast also setting up a simulation is. So talking about the methodology, as already mentioned, the Particleworks is based on the meshless MPS approach, so moving particle simulation approach. In this approach, as you can see, the fluid is discretized with particles. We don't have any mesh to be generated. In fact, the mesh is based on the particle itself. This methodology is very ideal when we have a lot of rotating elements because again, we don't have the mesh to deal with and it's very easy to set up the case. Also, when we have splashing phenomena or jets, it's very suitable. Here is another example. We have also a rigid body coupled with the fluid solved with Particleworks in this case. We also have a multi-physics solution like fluid, powder, rigid body coupled with the fluid. As I mentioned, contrarily to what is found in conventional method, we don't have a mesh, a static mesh on which we solve the basic CFD equation, Navier-Stokes and continuity equation. But we have this dynamic mesh. So the idea is that every little particle is representative of a certain amount of oil, a volume of oil, and we solve the usual equations with this Lagrangian instead of Eulerian approach. Okay, so a dynamic mesh that is able to follow the fluid flow. This methodology was proposed by a professor in Japan, Professor Koshizuka, that is also a co-founder of the developer of Particleworks, Prometheus software. So since the mesh generation and the mesh and the CAD preparation is not really anymore present with this methodology, you can see that the simulation workflow is significantly faster. In fact, in less than 1 day, we usually have a working setup. And when we launch the simulation, the algorithm behind Particleworks that are highly parallelizable can take advantage of GPU acceleration. So we can launch the simulation on graphic cards instead of cores. And we can usually see a very strong acceleration. So because of that, you can see that in what previously in some cases took more than a few weeks can now be simulated in less than in 1 day or surely less than 1 week. What are the applications that can take advantage strongly of this approach? As I mentioned, gearbox lubrication is the main field, the historic starting point for Particleworks, because you have rotating element, you have splashing, so you have all the basic, let's say, feature of a system that is highly compatible with Particleworks. Also, e-motor cooling is nowadays very important for the automotive industry. We have jets on the windings and all the critical elements, as we will see, and we can analyze very efficiently those with Particleworks. We have also the possibility to study highly viscous fluids like chocolate, glue, cement, and so on, because we can include different viscosity law. On that, we can also model grease, so a very, very, very viscous fluid, as you can see here for bearings lubrication. Bearings lubrication is very important. We also have another example here with the rollers moving on, with a specific rotation on top of the rotation of the shaft. We will see, we will not have time to go in detail on this model, but it's very interesting also to see the pumping effect of the rotating rolling just below here. Then we have hydroturbines analysis. This is also very interesting field. We will present some results in detail. and of course, civil engineering application for water management, as you can see here. So let's go in detail about the application and also the validation with experimental data. The first test case I want to show you and talk about is the analysis of the coupling gearbox found in this system. The application is a wheel loader, so we have this element that was analyzed with Particleworks in a collaboration with Comer Industry, one big Italian producer of gearboxes and axles. So the idea was to evaluate the lubrication of this system at different rotational speed and rotational direction, as well as also mounting angle. So we could also control the mounting angle of the gearbox. The target was to compare results from simulation with experimental data. So what is usually done in this kind of system is to build a clear casing, as you can see here, and it's to analyze the oil distribution visually. Of course, this requires this type of testing requires a lot of cost in producing and manufacturing all the clear casing, and also waiting times because the production is not instantaneous. We can see here a comparison between the simulation and the same system at the same load condition, and we can also quite clearly see very interesting relationships. We have the film formation in the bearings area here. We have very low lubrication on top, as you can also see in the clear casing. And overall, what we did in this project was to compare for the different conditions the lubrication degree in all the zones. And it was found that there was a very good agreement. So the numbers here represent very good or very bad in the case of one lubrication level. And by visually comparing the two, we could see across the condition very good correlations. On the e-motor cooling, we have a very interesting test case and confirmation with Ricardo. We collaborated with them on a project that and the aim was to evaluate the temperature distribution, especially in the windings area. So this is one of the most critical area in e-motor design for automotive application. Of course, we know that e-motor development is a very important topic right now, and the power densities in this kind of system are increasingly higher. And because of that, we really need to optimize the cooling, and that's why air cooling is not enough, and we want to introduce oil cooling above other type of cooling. So the results are also presented in a paper, a more detailed paper. If you want to have a look, we have the QR code here. So the idea is that what is the workflow with Particleworks for e-motor cooling? So we usually do the e-motor fluid analysis. We can transfer the transfer coefficient from Particleworks to the thermal solver. In this case, is Geomet, that also can compute the electromagnetic losses. So in this model, you have electromagnetic losses, you have the thermal analysis. You transfer the data from Particleworks to Geomet. We will see how efficient and fast is that step, because we have also developed coupling between the two software. And at the end, you want to understand what is the temperature distribution. So in Particleworks, the e-motor fluid analysis is also structured in different steps. We can do, as you can see here, the analysis of the rotor distribution in all the channels. We can also do a jet analysis after the rotor step is done. We can include windage effects we can include air. So of course, the rotor rotating will cause some air field inside. So we can also take into account that, of course. And at the end, the most important aspect is to analyze the distribution on the windings and in the casing of oil, and where accumulation is, and of course, the last objective is to evaluate the HTC maps on the windings or other critical areas, as you can see here. So from the accumulation of oil, we can extract the HTC maps. HTC maps are then transferred to, again, the thermal analysis, and temperature distribution are found. In this case, as I mentioned, we wanted to compare the simulation results with the experimental one. The objective was to find the maximum difference in temperature range between the simulation and the measure of 5 degrees. All points in the windings area that were monitored by Ricardo were actually found to be in a much smaller range, with a maximum difference of 2.8 degrees, as you can see here. So Ricardo was very happy with this validation and was well inside the range they expected. Piston cooling is, of course, another interesting application. As you can see, thermal analysis in Particleworks is really one of the main features that our customer use. So we have different studies also in this field. Clearly, also in this case, due to the moving parts and the jets impinging on the piston, clearly we have a lot of advantages over mesh-based CFD. We have one study with Wärtsilä, a company that produces large motors for the naval application, so very big pistons in this case. Wärtsilä compare also in this case with experimental data, finding very interesting correlations. And also HPA Cox presented last year or recently another comparison between meshless MPS and traditional CFD, and they found in this case was star CCM, and they found that MPS is 10 times faster than mesh-based CFD with very similar results. This is the visualization of the results for that type of system. As you can see, we have 2 jets impinging on the e-motor, causing, of course, the cooling of the piston. Ducati Corse is also our customer, is publicly. This is a public information, as they also published another interesting paper on how to optimize jet designs. We will actually see Ducati Corse Ducati Corse study here. So the idea is that they want to optimize the jet direction and shape to optimize, as you can see here, the HTC maps and the cooling efficiency in piston. So they propose different type of application with different type of splitting of the flow, and they compare the temperature distribution. Again, if you want more details, you can find them following the QR code or visiting Particleworks Europe website, where we have all the material. Hydropower production is very important as well. I can present you this benchmark in collaboration with a Pelton turbine manufacturer in Italy. Zeco is the name of this company. They contacted us to evaluate Particleworks because they actually use mesh-based CFD, but they cannot do with this methodology full turbine simulation. They cannot account the transient simulation. They they really take a lot of time to do Pelton turbine analysis with traditional methods. So they wanted to investigate whether Particleworks could be faster and more precise or similarly precise, also providing additional information like case jet interaction or jet-jet interaction, multi-jet analysis. So the system is schematized here. Those are the results from Particleworks. We have the rotating turbine and the two jets. As you can see, we simulate two jets, the entirety of the turbine, while traditional CFD needed to really split up the geometry and focus on a very detailed element and part of the turbine. Here we have the velocity field. We can see interaction, long-range interaction as well. And on the left, we can see a clip with the pressure distribution close to the buckets of the turbine. So those are the summary of the results, just to give you some numbers and idea of how fast Particleworks can be compared to traditional CFD. So traditional CFD for this kind of system required 3 working days. Particleworks for the preparation only 2 hours. And the simulation time was 70 hours compared to 2 hours. We simulated the double amount of the rotation angle approximately, and we simulated the complete turbine, while meshless CFD only simulated 4 buckets, four half buckets, sorry. The multi-jet analysis was not also feasible, and other consideration like casing interaction or jet-jet interaction were not possible. The absolute values of efficiency compared to the model theoretical efficiency was very similar and comparable. So results were approximately the same. Food and beverage is also a type of application we can have. For instance, we can study, let's say, filling, bottle filling, or other type of filling that are found in the food and beverage world. Another feature that we can take advantage of is the non-Newtonian viscosity law that we can include with Particleworks. Also, the thermal capabilities are important for sterilization purposes, for instance. So all of these features are promising for let's say, food and beverage application. I can give you some example also in this case. Here we have a bottle filling application. So of course here we do have a lot of free surface flow, also bubble inclusion during the filling. This is found to be very interesting and to be studied with Particleworks. We have, for instance, sterilization of food. In this case, we have a cheese sterilization, so we can study the jet of water or the sterilizer fluid on the cheese. We can see the accumulation and also study, let's say, the temperature distribution or the wetted surfaces during the sterilization. So we can really optimize the design of the sterilization machine and the jets with this tool. As an example, another example. We can also analyze extruding extruders or mixing system. In this case, we have actually this screw for oil production. So the idea is that we are here simulating beans, okay, of so solid material, not fluid in this case. And we want to, actually it's seeds, it's not beans. So we have seeds that we want to pressurize in order to extract oil. And we can clearly see the pressurization due to the screw effects. And we can optimize the torque and the mixing, precision, and so on. This just to give you some examples here of application that we had a look with customers. Okay, on the application, I think we are done. I'm going slightly faster than I would like because there are a lot of things to cover also for the demo. So here, just an overview of the additional features that are also and capabilities of Particleworks that could be of interest for you. I will go through them in a very quick way. So one feature is the finite volume air analysis. So the idea is that in this case, we can have a two-way coupling between air and fluid. The air domain is discretized with a grid, a Cartesian grid with a finite volume solver, so a very different solver from the MPS meshless solver. Everything is done in Particleworks in one simulation. And as you can see in this bottle pouring application, we can clearly see the coupled effect between air entering the bottle and creating bubbles, and also water that is, let's say, dynamically influenced by the air pressure field in the entrance. Another example is another feature of Particleworks is the ability to include an interaction, a fluid structure interaction in Particleworks. In fact, solids can also be discretized with particles, as in this example. So the turbine could be moved and made rotate due to the interaction of fluid. Okay, so as you can see here, the velocity field in this direction is positive because the jet is impinging and forcing the Pelton turbine to rotate, and everything is done in Particleworks also in this case. Another feature is the possibility to automate the scene generation, so the simulation setup with Python. So there is one module written on purpose for Particleworks, so we can control every aspect of Particleworks simulation with a Python module that is named PVPy. So in this example, we scripted with Python a gearbox simulation. We set up the numerical settings, the boundary condition, the geometry file were collected in a specific model folder. And after defining the physical properties of oil and so on, we could run the script, and the result was the creation of the project, the Particleworks project, with the import of the geometry and the definition of all the numerical settings. We can also, with the script, run the simulation without opening Particleworks and the GUI, and also perform the post-processing in an automatic way. So this can really speed up the reporting and the analysis of different configurations. So in this case, we plotted also torque plots, or we also prepared a PowerPoint report, including videos, just to give you an idea of what could be the possibilities. Another feature, and this is the last feature before the demo, and before discussing a little bit actually. So after this presentation of Particleworks, Didier will briefly present JMag as well, and then we will show you the demo of the e-motor, of an e-motor model, and we will show you all the steps for the simulation in this kind of system, and also to transfer the file to JMag. So the last feature I want to present you before JMag presentation is the visualization option. This is a software able to move results from Particleworks to a 3D computer graphic tool. So the idea is that, okay, you do the simulation, then you transfer, for instance, to Blender or Unity, this 3D computer graphic tool. You transfer the results and the simulation. In this way, you can do very nice renderings of your simulations for visualization purposes or also marketing purposes. Actually, the output that we get from this kind of 3D computer graphic model can be a video, but also a virtual reality environment that could be accessed by a VR viewer like Oculus. Okay, so we could we could inspect the results from our simulation with the VR tool. Okay, so that's all for my part for now. I think at the end we will, so if you have questions, please write them down and we will do a Q&A at the end of the presentation.
Okay, so thank you, Michele. So I think now you can make me presenter. So if you go to the panelist, you right click on my name and you select make host. I will be able to share again my screen. Okay.
Yeah.
So let me know if you can see my screen. Okay, so I will then go to the next part about Geomet designer that we have used, that I used to make some thermal analysis. Okay, so I will go quickly first into Geomet. Not that you will have several analyses. So the first analysis is this magnetic field analysis, where you will be able to analyze the electromagnetic field distribution inside your electric motors. You also have thermal for temperature analysis. You have electric field for current distribution analysis. You have structural analysis for mechanical deformation analysis inside your motors, and you also have the iron loss calculation analysis. So the other advantage of Geomet is that you will be able to couple all this analysis in order to make a multi-physics simulation. Okay, so regarding the different application motor type that we can simulate with Geomet, so we have a generator, transformer, so all type of electromechanical system can be simulated with Geomet. And inside Geomet, we have a lot of feature to model with more precision the motors. So regarding the loss calculation, so we know that into the electric motor, it is very important to know how the heat is produced and how this is converted to a temperature. So for that, Geomet are able to calculate different losses. So Geomet are able to calculate, for example, the iron losses due to the variation of the magnetic field inside the steel sheet of the motors. So you will able to get the hysteresis loss and the education loss into the steel sheet. You're also able to get the loss into the winding. So the copper loss got the losses into the tray or the tank of your motors due to the variation of the eddy current. Okay. So to make a thermal coupling using Geomet and Particleworks, so here you can see the process that we can follow to make this kind of multi-physics coupling. So into the Particleworks, so you will able to create the fluid flow analysis model where you will run the simulation and get the HTC distribution into your structure. Then the HTC distribution can be export into a CSV file that you will be able to map into the thermal analysis model of Geomet. So this is the process to create the Geomet model. So we will start by calculate the Joule loss, so the loss inside the motors. Then after getting the loss distribution, we will try to build the thermal analysis model where we will add some condition in order to map the distribution of the SCC into a specific pair. Then we will be able to run the calculation and get the result. Maybe I can show you some demo. Okay, so this is an example of electric motors. So you have a different part. You have the tank, the case. You have the stator here. You have the coil. You have the rotor with the aluminum bar, and you have the shaft with the bearing. Okay. So here I can show you the result of the cooling simulation into Particleworks. So this is the cooling here, and I can also so this is the distribution. So you can see the distribution of the HTC coefficient on the fluid. So this distribution of the HTC can be extracted using the mapping function here. So into the mapping function, you will able to define the setting to extract the HTC of a specific part. Yeah. If I show you the model into Geomet, okay, so this is the Geomet interface. Yeah, so here you have the project manager, which will contain all the model 2D or 3D model with all the study that you will create. And from your right side, you will have the toolbox. So the toolbox will contain the material database, the specific condition that you can apply to the study. You also have some script template where you can save your script, because in Java you can use several different type of scripting language like Python, Java, Visual Basic, and you can also use MATLAB to control Java simulation. You also have a database to save all the setting of the other setting that you can also save here, and also variable and some picture of your project. Okay, so here regarding this 3D model, so this is the 3D model. You have the same model here. So if I right click here, you can see the different analysis that you can apply to this 3D models. So in order to calculate the losses of the motor, I use transient analysis, or you can also use frequency analysis if you want. Then here I run the simulation. Here you can see that I run the simulation. First, I define the material of each part. Here, I define also some condition. So, for example, to calculate the torque, to calculate the losses, and to define the winding connection here. And this is to extract the heat losses of each coil here. I can also show you maybe the result of multi-field analysis. So this is the distribution of the multi-field analysis. I can show you the distribution of the Joule losses of the coil. So here you can see the Joule loss of the coil, and also the iron losses of the rotor and of inside the rotor and stator. Then after you get the losses, then you can create now the thermal analysis here. Into the thermal analysis, you will define the material, where you will define also the thermal property of each part. Then inside you will define some condition in order to model the thermal behavior that occur into this machine. So here you can see that I defined some heat transfer boundary condition in order to model the interaction. So the heat transfer interaction between the core and the air region. So for example, the heat transfer condition between the coil and the oil, I will use this, I will apply some condition where I will define the reference temperature, and then I will import the HTC distribution that I have calculated from Particleworks. So this is the HTC distribution specify that I get. So with that, I will be able to run the simulation and get the temperature distribution. So here I will get the temperature distribution on the coil and also on the rotor side on other parts with more precision. Yeah.
Yeah.
Okay, I think it's good for me.
Yeah.
I will...
Exactly. Thank you, Didier, for
yeah.
your presentation. I want just to take one step back and have a look how to build the Particleworks project. Okay, so because Didier correctly showed you the e-motor model that we built here, I just want to give you an idea on how fast we can get to this working model with Particleworks and what are the steps. So let's create a new scene in Particleworks. A scene is basically a simulation. Okay, so what we want to do is to import the models. Okay, so we can import all the models, maybe not the duplicated. So those are STL's models directly exported by the geometry, so by the CAD. So we didn't need to do anything on these STLs. Okay, so we have bearings, the casing, we have the coils, and so on and so forth. Okay, so these are the bearings, the shaft, rotor, and cages, and so on. Okay, so we can of course change the color of some of these elements if we want, but yeah, that's all. So the next thing we need to do is to define the inflows. We have let's say 4 inflows on the two sides, so 2 and 2. So to do that, we can define a circular inflow. The width is 8, 8. We have to position it. I will just go through these values that I note down. We can also, of course, import an inflow position from the CAD. So this is one inflow positioned correctly in theory. So we can duplicate that inflow and adjust some settings. So we have 1, 2 inflow. Okay, and then those 2 inflows are like that. Okay, so in this way we created all the inflows, just idea. Then what we do is to create the fluid properties. We have oil, of course. Okay, So we define the surface tension coefficient, also the contact angle, if we want. We need to define the wall. So in this case, it's just one slip, no slip boundary condition that is isothermal everywhere for this kind of application. So just for this tutorial, we stay there. We can also define different temperature, do the thermal analysis in Particleworks, but for now we just focus on the temperature independent HTC extraction computed by considering Nusselt correlations. Okay, so we created the fluid and the polygon. We can assign oil to the inflows and shaft. So to the walls, we define a wall boundary condition. Then to make the bearings and the rotor and the shaft rotate, we needed to define a group, rotating group. So the rotating group, we can make it rotate along Z with a certain RPM speed. It's, for instance, 2,400. Then we select all the elements that need to be rotating, and those should be rotor, shaft, squirrel as well, maybe. Okay, so those one. So in the properties, we can define a parent, and we can set rotating as a parent. So everything that is in the rotating group now rotates, as we might see. Maybe slowing down a little bit this simulation, this preview interval. So as you can see, it's not quite clear to visualize that, but the rotor and the shaft is clearly rotating, okay? Okay, that's more or less all, I think. We just need to adjust the domain. This is the simulation domain that at the beginning of the simulation is initialized in a very specific region. If we adjust the domain, basically it will, so everything that is inside the box will be simulated. So particles can exist inside the box, basically, okay? Okay, that was done as well. Now, I think we just go through the numerical settings. We just change the units. Particle size in this case is basically the mesh size. It's a 0.7 millimeter. The gravity is in Y direction. Explicit solver for pressure. I'm just inputting basic values, or actually values that I pre-calculated here. So viscosity explicit, surface tension model, one standard one. And then heat transfer coefficient, we want to extract an HTC that is again temperature independent. We don't do any thermal analysis or conjugated heat transfer analysis. We just extract HTC from Nusselt correlations, basically at this stage. Then we set the finish time, that could be 2 seconds, and the initial DT, that should be around 4e-5. File output interval time is how frequently we save and how frequently we do the load torque analysis. Okay, so we take a picture every 5 milliseconds. Okay. Yes, that should be more or less everything we need to do, just some advanced feature and options, current limiter, and this parameter that has to be changed. Okay, so we have everything set in 10 minutes or so. We can do the pre-processing and simulation that will be done on an NVIDIA graphic card, the simulation. So let's see if I did everything correctly or if I forgot about something. So in the pre-processing, the software will discretize every STL with a specific grid. Okay, so the idea is that we will create a grid, a Cartesian grid, representing the surface. Okay, and this grid size, it's usually in the range of the particle size or a little bit less. Okay, so in here particles cannot be, but of course here they can. So yeah, in this case it's doing the distance function. This is the name of the function that I just presented to you. Distance function of one STL. We will do for all the STLs, and then we will have some results that we can inspect while the simulation runs directly in Particleworks. Yeah, let's wait a little bit, or maybe we can also have a look at other results that we should have around, as already discussed with Didier. So basically, after a little bit of waiting, we will have this kind of information. So we see, in this case, 6 jets. We have droplets going down, a little bit of accumulation of oil. And then if we want to have a look at the map, we can see the map. Let's see if we have the map somewhere, or otherwise we can generate the map as also Didier explained. So we can take maybe the last frame, last few frames. We have to assign the model for the mapping. In this case, we focus mainly on the coils. We do an average over the 3 or 4 frames. And yeah, so this should do it. We will see a map of the HTC on the coils, an average map. That is basically what is then transferred to GMAG. Here the preprocessing is still going, as well as the simulation, the mapping. Okay. While we wait, maybe we can see if there are questions or curiosities, perhaps.
Yes, so thank you for this demonstration. I think, yes, we can switch to the question. Let me check if we have some question. So that there is no question there. No question. Okay, as that there's no question, so I think we can end this this webinar.
Yeah.
So thank you, Michele, for this good presentation and good demo.
You're welcome.
And
thank you.
Yes.
Thank you all for being here.
Yeah. And feel free to, if you want to get more information about Particleworks, so feel free to contact us by email if you want. Okay, so thank you and bye.
Thank you. Have a nice day.
Bye. Yeah.